Hi everyone, welcome to Lesson 7. In this lesson we're going to dive deep into the details of quadratic relations. So let's just review some of what we already know. We know that if we graph a quadratic, the graph is a curve. Furthermore, we know that if we look at the table of values and examine the second differences, they're constant. We know that if we look at the graph, depending on how it's formed, it will either go up and then down, or it will go down and then up. The point where it changes direction is either a maximum value, if it's at the top, or a minimum value at the bottom. And it seems to have a shape which is symmetrical. Okay, so that's basically what we know so far. We also know a few bits of vocabulary which we've discussed in class. Okay, so let's just quickly review the rule of 3 for quadratic relations. We know that if we have our graph in its equation form, that the a value, the coefficient of the quadratic term, tells us whether we're opening up or down. So we call that the concavity. It's either concave up or concave down. It also tells us kind of how what the graph is shaped like. So whether the graph is wide or thin. We also have in the equation the y-intercept, which is the constant value we normally write at the end of the equation. Okay, going to the table of values, we can work out the first differences, and we know from experience that the first differences in a quadratic are not constant, right? As you can see here, these numbers in the first differences column, those are not constant. However, if we then go ahead and do our second differences, then we get constant values. So those second differences tell us that we have a quadratic because they're constant. They also tell us whether we're concave up or concave down. So in this example here, you see the second differences are positive 2. This would be a graph that's concave up. Quadratics tend to show up a lot in the real world. Mostly we do things in sort of architectural sort of frameworks. So for instance, you might have a stadium, or what is that, a hangar or something. You might have the inside of a church perhaps, or this is the St. Louis Arch. Speaking of arches, you might go to McDonald's and then you have the golden arches, or you might have some kind of a bridge-like structure. They also show up in a few other random places. So for example, if you look at the flame of a Bunsen burner, for instance, you could describe that using a quadratic, like the bottom of the flame here. You see that? It's kind of a quadratic. Also, if you take a cone and you saw through the cone at an angle, what you'll actually produce is a quadratic. The face which you cut will be a quadratic. And I guess it kind of shows up occasionally in other things. For instance, if you have a ball bouncing here, this is basically a ball which bounces off the ground and then comes up and then down. It will trace out the shape of a quadratic. And then I'm not quite sure what this is. It kind of looks like a metronome or something. That's kind of a quadratic shape. So that's some examples of quadratics in quote-unquote the real world. Okay, so let's just switch tacks back to some terminology. Some of these we've already seen before. In fact, you should be getting comfortable with most of these. So you know that in a parabola we have the special point called the vertex, which is the point where the parabola changes direction, either from up to down or down to up. If the parabola crosses the x-axis, those points where it crosses are called the zeros, or the x-intercepts, or the roots. So for whatever reason, they have lots of names. Okay, so those are the zeros. Not all parabolas have x-intercepts, but many do. Okay, and then we have this word concavity, and so concavity is basically tells you the direction of the opening. So when you have a situation where you're concave up, then that's the case when a is greater than 0. Right? Your a value is greater than 0. Or when your second differences are greater than 0. Okay, so both of those situations really mean the same thing. And at your vertex, you have a minimum value. Okay, you have a minimum value of y at the vertex. Conversely, if you're in the concave down situation, a is less than 0. And the second differences are also less than 0. And in this case, your vertex is a maximum value. Okay, so there we go. That's basically the difference between concave up and concave down. A parabola is symmetric in the last lesson when I was talking about parabolas, the shape of a parabola, I mentioned that they're kind of, it can look like a mirror image. So if you imagine a dotted line which cuts through the middle of the parabola, which I've drawn here, that acts like kind of a mirror. And it actually has a special name called the axis of symmetry. Okay? And the axis of symmetry always cuts through the vertex. So the vertex is the only point which doesn't have a mirror image, essentially. And then one last thing, if you want to talk about the equation of the axis of symmetry, it's always just, so you know, it's a vertical line. So the form of a vertical line is always x equals number, where the number is the value of the x-coordinate of the vertex. So in my example here, the axis of symmetry would be x equals 10, because my vertex has an x value of 10. If you look at a graph, the axis of symmetry can help you do a few things. It can basically help you save a little bit of work. For instance, if you look at this graph here, you can see that here's the vertex, right? It's the point where the graph changes direction, and consequently, here's your axis of symmetry. That is at x equals 1, okay? Now, what this graph is basically trying to show is that there are always going to be 2 points symmetrically spaced around the axis of symmetry. So here, for example, I think I have 0, 9, and here I have 2, 9. Let me just write those in. 2, 9, and 0, 9. Over here. Okay? And what you can see is that those 2 points have the same y value. So that's really what it means for points to be symmetric. They have to have the same y value, and they also have to be the same distance away from the axis of symmetry. If I look at 2 more points, I can go down here to the zeros, and I see that this 0 is 3, 0. But this other one is -1, 0. So once again, the y values are the same, 0, and the distance away from the axis is the same. Right? The distance away in this case is 2 units. The distance away in this case is also 2 units. Looking at a table of values, again, this can be a little tricky if you're not used to it, but basically what you're looking for is you're looking to see the pattern in the y values. Remembering that symmetric points always have the same y values, right? We saw that on the graph. You're basically looking for points in the table which have the same y value. So for example, this one and this one both have a y value of 0. And this one and this one also have a y value of 0. So since there happens to be a point in the middle of those, this one, which doesn't have a mirror image, then we can say that this one here that I've circled in blue has to be the vertex. So that's basically how you can find a vertex from a graph and a table. Now, I didn't talk about the axis of symmetry for the table, but I think without too much argument, you can agree that the vertex here, since it's 3, -2, the axis for this table would have to be x equals 3. Again, because our x-coordinate of the vertex is 3. So that's what that one goes. All right? That's basically it. I want to leave you with a joke. Wouldn't life be interesting if there were more math in everyday situations? People always ask me that. When am I going to use this math in real life? Well, imagine if you were driving along, or well, I guess your parents were driving along, and they saw this and they had to work it out. You know, that could make for some very interesting driving. So maybe it's probably best that our speed limits are just a little bit easier. I don't know. Maybe people would be better at math. They'd take it more seriously. Anyway, have a great one, and I'll see you in class.